High-value placer gold is the ultimate objective in fluvial exploration. These are heavy, high-purity nuggets, often concentrated in the lowest layers of a river system. Identifying these deposits requires a total departure from primary hard rock models. While a primary orogenic deposit exists as a concentrated vertical vein, placer gold is the result of that vein being pulverized and scattered horizontally across massive, heterogeneous gravel beds. Because this metal is dispersed in a thin sedimentary sheet, it lacks the physical mass to trigger a direct geophysical response. It produces no density spike for gravity instruments, no magnetic pole for sensors, and no distinct spectral signature for satellites. Exploration methods built for primary deposits generally overlook these areas. Sensors calibrated for massive sulfides or magnetic bodies pass over high-grade placers without detecting a change in the background noise. Mapping these targets effectively requires a multimodal data stock. By layering topographic, radar, and potential field data, geoscientists can analyze the environment for the physical conditions that force gold to settle. The strategy shifts from searching for the mineral to searching for the geological container that perfectly trapped it. Placer formation begins when weathering and mechanical erosion strip primary gold from its host rock, liberating the gold into a high-energy fluvial transport system. We use DEMNS, digital elevation models, to map the fluid dynamics of this transport. By analyzing the elevation, we can determine exactly where the terrain forced the water to lose its carrying capacity. We isolate regions with a slope between 0 and 10 degrees and high flow accumulation. These represent the transition zones where a river slows down, allowing heavy sediment to drop out of the current. Calculating the topographic wetness index, or TWI, adds another layer of precision. High TWI values indicate the specific depressions and flats where water and sediment naturally pool over time. In tropical environments, however, optical elevation data hits a limit. Dense forest canopies often hide the very features we need to find, such as subtle river terraces and abandoned channels. Sentinel-1 SAR, synthetic aperture radar, provides the solution. Radar waves penetrate the foliage to map the texture and moisture of the ground surface directly. We look for a specific SAR signature, low to medium VV backscatter, low VH, and a high VV-VH ratio. This signature isolates fine, bare alluvial sediments. It allows us to pinpoint the point bars in paleochannels that are otherwise invisible to standard optical cameras. We also look for macro features like distal alluvial fans. These indicate a massive, sudden drop in flow energy, identifying the exact zone where the heaviest materials would have been the first to settle. By integrating DEMNAS and SAR, we map the hydraulic energy of the landscape, identifying every location where the river's velocity dropped enough to deposit heavy minerals. Because of its extreme density, gold is hydraulically sorted alongside a specific suite of heavy minerals that share its transport characteristics. These minerals, magnetite, ilmenite, and hematite, form dark, heavy sands. Where these minerals accumulate in high concentrations, gold is likely to be present. Ground geochemistry reinforces this link. Placer anomalies with over 20 parts per billion of gold consistently correlate with iron levels above 5% and titanium above 1%. We map this iron-rich proxy from orbit using Sentinel-2 and principal component analysis. We use bands B2, B4, B11, and B12 to isolate iron oxides and clay signatures. Combining these bands into a PC4, PC3, PC2 composite separates target minerals from soil and vegetation. In the final RGB output, sediment rich in Fe oxides appears bright red, providing a visible proxy for heavy mineral concentration. This multispectral signature serves as proof that hydraulic sorting has occurred, successfully concentrating high-density materials in that specific location. Modern geomorphology cannot account for ancient river systems that have been buried under hundreds of meters of recent barren sediment. The highest-grade deposits are often locked in these hidden paleochannels. We use gravity data to map this buried paleotopography. When a valley carved into dense bedrock is filled with lighter sediment, it creates a detectable density contrast. The Bucher and residual gravity data show a distinct low. The meter records a dip in gravitational pull, exactly where sediment fill is thickest. We then apply the first horizontal derivative, highlighting the edges of the gravity low, marking boundaries against steep bedrock walls. The second vertical derivative further clarifies the shape, pinpointing the center of the channel, where the sedimentary container is deepest. Geomagnetics provide the final subsurface check. While the general sediment fill yields a magnetic low, we look for localized high anomalies within that channel. These localized magnetic highs indicate buried pockets of magnetite and ilmenite. They act as high-density markers within the paleochannel, pointing to the heaviest part of the sedimentary load. Potential field geophysics allow us to map the structural walls. The target is the contact zone, where the ancient riverbed meets the bedrock. Here, water's energy hits zero, locking heavy gold particles into the fractures. We must distinguish this pay gravel layer from the conductive clays above it and the barren bedrock below it. Geoelectrical resistivity reveals the stratification. Different earth layers resist current based on moisture and minerals. We look for a moderate resistivity layer, 100 to 500 ohm meters, representing pay gravel, positioned directly atop highly resistive bedrock. To confirm the presence of heavy minerals, we measure the chargeability, or IP. While gold itself has no IP response, the minerals it travels with do. Trapped minerals like pyrite and magnetite produce a chargeability response. A low to moderate IP anomaly between 2 and 10 millivolts per volt within that gravel layer confirms the presence of a heavy mineral trap. Resistivity and IP provide the exact 3D coordinates where the ancient river's energy was completely spent, identifying the microenvironment for gold accumulation. Operating with a single dataset in this environment leaves an explorer vulnerable to false positives, geomorphic features that look promising but lack the internal traps required for gold to settle. High-precision targeting requires a vertical overlap of signatures. On the surface, we require high TWI and high flow accumulation to identify the geomorphology. Beneath that, the gravity and magnetic data must confirm the presence of a structural paleochannel to host the deposit. Finally, at the base of that channel, we must detect resistive gravel with an elevated IP response. When all three anomalies intersect, we have a scientifically grounded drill target. This multition by verifying the physical history of the site. In the hunt for placer gold, we do not find the metal directly. We find the precise geological and hydrological container that trapped it.